Okay, so this chapter is simply about the history of additive manufacturing. We will discuss some milestones in the additive manufacturing field, what's happened and what is happening right now, and what will happen in the near future. So I would like to start with a brief video. It's not obviously directly related to additive manufacturing, but a nice one showing methods where they use additive manufacturing to embed QR codes into the parts, into the products, and they use additive manufacturing technology. Yes, this is a QR code, and they simply project on it. And this was the final project of, I think, 2018. I gave this project to the students, and one group did it great, and we have written a conference paper about this one. We use a simpler approach. This one is a bit complicated, but our approach was much better, I guess. And we could easily read I have, yes, square. I will try to show the output. I'm not sure whether you can see, but we achieve embedding actually QR codes into the products. If you see that inside this part, we have a QR code. It's not visible if you don't have light, but inside it, we have a light, so we could actually embed some information into the 3D printed parts. Here you see by using such a QR code, they are able to give a link to a website, give a message. They also do it with a casting operation. They have chocolates. This another wax model. This another tablet, pharmaceutical tablets. So by checking the tablet, you can easily see what it's used for. So let's start the actual, let's say, history of additive manufacturing. Obviously, it's the result of some various technologies. If we didn't have, let's say, computers, we wouldn't be able to obtain additive manufacturing machinery. So we will also consider these key technologies in the field and then go into details of the additive manufacturing. But we can, they were invents around 1980s, and you can imagine how it was difficult in those days, to improve, to develop such additive manufacturing machinery. They even didn't have powerful computers. They didn't have powerful lasers, sensors, microcontrollers, but they were managed to obtain such a machine. So this is the first technology actually we need in additive manufacturing systems, the computers. So why do we need to use computers? First of all, we need to have some processing power. Processing power for, let's say, support structure generation, processing power for doing the slicing in the CAD software, and also we need to have the graphics capability. We need to design parts, we need to orient them in our manufacturing software, and we need also computers to have some control on our actuators. We need to have some closed control in some critical parts, especially access control, temperature control. And we need to have the networking capability of computers. Why is that? Since if you have multiple printers, multiple computers in your office, in your factory, then you need to have proper connection between each computer and each additive manufacturing machinery. And these days, even we can submit our machine files over Wi-Fi or from, let's say, one city to another city, or from one country to another country. Another thing we use computers is for integration of these smaller parts, since we can gather information from different parts, different actuators, different sensors. We gather these information and process them in the microcontrollers in the computers. That's how we do the integration with the help of computers. So in summary, we can say that computers are highly important. If we don't have such improvements in the computer technology, we don't have powerful let's say, additive manufacturing systems. This is actually kind of a schematic showing the structure of additive manufacturing machinery. For most of the time, we have process control. This is actually the heart of the additive manufacturing system. And as you see, we give inputs through a user interface. This is graphical user interface. For most of the time, the users do some setups, do slicing, generate the support structures, and also monitor the, let's say, the states of the printing process with the help of some numbers here. So this is an overall interface, user interface in the additive manufacturing machinery. And as we mentioned, sometimes this is connected to the LAN or WAN. This actually information is conveyed to the network so that people at different offices at different cities can monitor the situation of the fabrication process. And if you consider the process control once again, this, as I said, is the heart of the system. We have many sensors connected to here. We acquire information from the printing area, the temperature of it, the humidity, the pressure sometimes. We control the, let's say, some extra equipment like coating. If it's a powder-based system, the coating is important. If it's a special hat, we may sometimes have cleaning units. We control them with the help of this microcontroller unit. And we also control the axis, the position of our axis in Z or XY. So we do it with the help of, again, this controller. And furthermore, our controller gives actually commands to the actuators and acquire information from the sensors. So this is a summary of the structure of additive manufacturing machinery. We have the main units as kind of microcontrollers or computers, and then other units are always connected to this controller. And on the host side, on the user side, we have an interface. And on this interface, users can do many things: start the process, stop the process, adjust the parameters, set the slicing thickness, set the infill percentage. And on the other side, this is the machine side actually. Let me show it like this one. This whole part is machine side. And these actuators and sensors are controlled with the help of the microcontroller, mostly inside the additive manufacturing machinery. Any questions, guys, up to now about the improvements, the, let's say, improvement or importance of the computers in additive manufacturing? So then let's focus on the other technology actually we need to have in the development of additive manufacturing is the CAD technology. So where do we use CAD technology? We use it for designing large buildings, and also we use it for designing of micro-scale, nanoscale microcomputers, microprocessors. But for additive manufacturing, we use simply mechanical engineering software, CAD software, and we are trying to generate, design some forms, some parts. And the CAD was first developed, but later people developed into complete manufacturing software. And due to the requirements in the manufacturing side, they pushed actually the CAD side to improve. Since CAD wasn't actually that powerful, they couldn't respond to the needs of manufacturing software, and then that's why many people, researchers, focused on the development of CAD, and now these days we have much powerful CAD software which are responding to the needs of CAM software. So in most of the CAM software, what are we doing? We are simply producing G codes, and these G codes are mostly for 2.5D shapes. If you consider, for instance, the CNC machining, although it's called as 3-axis CNC machining, the sub-steps, the sub-manufacturing operations are mostly 2D. For instance, if you just consider drilling, we can even assume that it's the 1D operations. Once you position it properly, the workpiece, and your drill tool will go into the workpiece and do the drilling operation. But for other cases, for let's say face milling, what we do, we simply cover the surface. So you can assume that it's a 2D operation, but since for most of the time we are doing it at different elevations, we can name this process as 2.5D machining. And over you see this NC machining, numerical control is based on the surface models you have done in the computer design software. And with the help of this design software, we can do machining, and also these days we can also do additive manufacturing. So what do you think? In the earlier additive manufacturing applications, people had some difficulties. And what do you think, what was the main difficulty? You can unmute yourself and answer this question, guys, or you can simply write it in the chat area. So what do you think? What was the main difficulty in the early additive manufacturing applications once they were using CAD software? Do you remember we discussed about the STL conversion? People were...
It's Yusuf speaking, Yusuf.
Yes, Yusuf, go on.
Well, the surface modeling in the CAD softwares is soft. You just make the surface as perfect almost out of the finishing. But the additive manufacturing side, the modeling of the layer by layer was a difficulty for the program, I believe.
Somehow, yeah, but we may have another answers, maybe. Anyone willing to answer? Have a different, let's say, answer? We have some...
Maybe the microcontrollers weren't as powerful.
No, we are talking about actually the software, the CAD and CAM software, mainly the CAD software. Why we had some problems in the CAD software? So what do you think? Is it important to have a watertight model in the CAD, let's say in machining? Think about this pyramid. Is it highly important if I have a perfect, let's say, tight model, watertight model? Since what you do in machining, you start from a solid, let's say, workpiece and then do some subtractive operation. But in the additive manufacturing, we start from nothing, we start from scratch and try to extrude or try to jet some powders and try to join them together. So if you have problems with your CAD design, most probably you will see these problems in the printed products. But if it was CNC machining operations, you cannot see it since you start from an initial workpiece, it's already solid, it's already filled with material, and you simply remove material. And in the earlier, let's say, CAD software, they were not working on a very watertight models. Watertight means that if you, let's say, put some water inside, then there might be leakages and you will not be able to contain the water inside. But in additive manufacturing, this is a must. Your models should be watertight. Once you do STL conversion, once you convert your design into a mesh format, you shouldn't have any openings between the triangles. They should be exactly on top of each other or be neighbors exactly. Otherwise, once you take the slices, you will have some weird lines. So this was the main challenge, main problem in the earlier CAD software, but nowadays, most of them have solved this issue, and once you do the STL conversion, you mostly have a watertight model. But still, if you cannot obtain it, then what you do, there are some repairing tools, repairing software, STL repairing software. You import your STL software into these software and then try to solve your problems, try to fill some empty regions. So that was the main for the difficulty of people having in the earlier days. So let's recap what we have discussed for the CAD technology. So we are preferring to have a solid modeling for additive manufacturing, and these days we even have some online CAD software. You don't need to even install the CAD software into your computer. I know one of them is called Tinkercad. Do you know any other online, let's say, CAD software? So what you do, you simply open up your browser and start designing. Do you know any other ones other than Tinkercad? Has anyone designed a model, let's say, online on such web browsers? No? It's an interesting tool. You may have a look at it. Without using, as I said, a powerful CAD software, you can simply do it in your browser. So now what kind of improvements we have in the CAD software? With the improvements of graphics card and CPU technology, we have some realistic features. They are more realistic than ever. We have much powerful interfaces. They are much user-friendly. You can do whatever you like. You can do parametric design. You can have complicated assembly. So we have much powerful CAD software these days. And even in some of these, we have engineering contents embedded. We can perform some simple complete engineering analysis, finite element analysis, and they are much faster these days. Their speed is better. Their accuracy is much better. You can design more complicated designs easily. So these are the main advantages of the novel CAD software. So what about slicing? We said that slicing is one of the main steps in additive manufacturing. So we should be able to do the slicing properly. But if you remember, we do the slicing in the design and fabrication pipeline. We do the slicing after converting the STL file. We do it in the CAM software. But some specific CAD software has also capability of doing slicing inside them. You don't need to convert it to an STL file and then do the slicing in CAM. Rather, what we do the slicing in the CAD software itself. And this is called as direct slicing. Since we are not slicing it indirectly, we are directly slicing the original design file, not the converted design file. But the problem is that since we have many CAD software, they use different, let's say, data structure for their designs, and their slicing software, slicing approaches are totally different. So they need to develop a specific slicing algorithm for themselves. Another problem is that if they are working with a specific, let's say, additive manufacturing machinery, then they should also write a post-processor for the specific AM system. So this is actually the main challenge, and that's why people prefer to use STL as an intermediate language between the CAD software and additive manufacturing systems. Let me have a kind of a box here, and we have an STL in between here. And we have other box here. This is AM systems. And we have many AM systems, okay? I'm not going to write anything here. And these are CAD systems. So if you didn't have an STL, let's say intermediate language, intermediate file format, so what we should have done is that for each CAD software, we need to write a post-processor for all these, let's say, additive manufacturing machinery. But once we have an STL, so it's much easier. What we do we simply convert our design files into STL, and then each actually additive manufacturing machinery accepts STL files, So things are much simpler. If you have an intermediate language, you can assume that this is English, so everyone speaks English, and we can do whatever we like. But if you want to do direct slicing, then you need to write post-process a specific slicing software, slicing algorithm for the specific additive manufacturing machinery. And if you want your CAD software being capable of working with many types of additive manufacturing machine, then that means you need to write n numbers of post-processes and numbers of develop and numbers of algorithms. So that's why people prefer to use such an intermediate file format. We'll discuss the problems about this file formats in our next chapter, but here you can assume that this is a nice approach for solving the difficulties here. But as I mentioned, we will be discussing the problems in the upcoming chapter. But still, although, as I said, I'm not happy, for instance, as a professional, as Murat mentioned, I'm not happy with the STL file, but I'm still, and I have to use an STL file these days. And that's why we call it as a de facto standard. It's not an official standard, but most people, most professionals in this field are using this file format just due to these practical problems. And the biggest challenge is that it's an approximation. Since we are converting the original design into an surface approximation by using triangles, we cannot exactly represent the original design. We represented it just using triangulations. We have a question. Yes, we can say that Murat is asking whether the top one is faster. Yes, it's faster, but you have to spend time at the beginning of your, let's say, implementation. Once you have this algorithm, once you have this, let's say, post-processes for your additive manufacturing machinery, they are faster and you have much more freedom in the direct slicing. We'll discuss these in the next chapter, but I can say that, and I prefer, in my research, in my lab, we prefer to use such an approach. We love to do direct slicing. And another question about the quality. Yes, the quality is much better in direct slicing since we said that the STL file is just an approximation. We can have much freedom, much accuracy with direct slicing. This is an example of an STL file, actually part of an STL file. I'm not going to discuss the details right now since we will spend maybe some hours, maybe 2 hours on STL files. So I can briefly here say that in STL files, we should have the information for each vertex of the triangle. This is a single triangle. We have vertices, and we need to define the coordinates of each vertices. These are the vertex information, and also we need to define normal, and the unit normal information is written here. So in STL files, you have to define these 4 parameters for all the triangles. That's why once you have too many triangles, the size of the STL file increases. As I mentioned, this was an approximation. Here you see this is our original design. Once you do the triangulation, you obtain such an approximation. And you can increase the number of, let's say, triangles. Once you do that, the accuracy will be much better, but the size of your file will be increased. So this is a kind of a trade-off. It's up to you. It's up to your application. You can set your, let's say, number of triangles yourself. But in summary, I don't like STL files. So no to STL. This is mine, not mine, but this is the motto of many professionals in the field. You can have a look at posts here on this web page. They're also discussing the disadvantage of STL file and they also discuss why they are using direct slicing methods. And as I mentioned, next week we'll be discussing the details of these issues, problems with the STL, and I will show you some examples, some fundamentals of STL files. I think we have another question. Yes, even though you have the vertex information in 3D, you need to define the normal vector. Since by using normal vector, you define which side is actually the outer of the part. But for instance, if you have such a normal, then that means the opposite of the normal is the interior of the part. This is an important information for us. If you define the normal interior, then I will assume that the interior of the part is the opposite of the normal. So that's why for each triangle, we need to define the normal and the vertices. So what are the other technologies we need to have in additive manufacturing machinery? First of all, depending on the technology, whether it's an SLA or SLA, we need to for sure have lasers. And for jetting technologies, we need to use some printing technologies. And for the control of the additive manufacturing machinery, we need to use such programmable logic controllers or microcontrollers. Another technology we need to use is the material technology. Since we are using very specific material, we are using powders, some gels, some resins, some special thermoplastics, thermosets. So the improvements in material science is quite important for additive manufacturing systems. And also for positioning, the improvements in CNC machining is highly important, since we have some similar, let's say, technologies for the axis motion, the control of these axes in a simultaneous manner. That's why we also depend on the improvements on the CNC machine. This is an example for printing technology. It's a jetting head. As you see, we have some thousands of nozzles and they are jetting metal at the same time. So we need to have such a technology for the jetting type of additive manufacturing systems. I think it's better I stop at this point. If you have questions, I would like to answer them right now, and then we can call it a day and continue the remaining of this chapter on Thursday.